The practice of a human developer writing software line by line with the help of a basic AI assistant is functionally obsolete. In early 2026, software engineering transitioned to fully autonomous, multi-agent orchestration systems. Instead of suggesting the next line of syntax, these AI systems now manage complex, long-horizon software lifecycles entirely on their own. Because modern development relies on orchestrating these digital teams, raw token generation speed is no longer the primary metric for success. Engineering leaders are now measuring innovation capacity, a metric prioritizing a system's ability to affordably and reliably execute complex logic over typing speed. This chart maps out exactly why that shift occurred. While you can see the generation speed of these models plateauing flat from 2024 to 2026, the cost of agentic execution branches into two drastically diverging paths. This split is driven by a three-way competition capturing the market: OpenAI's GPT 5.2, Anthropic's Claude 4.6, and Moonshot AI's Kimmy K2.5. Engineering leaders now face a strict dilemma. They have to decide whether their codebase requires cheap, massive parallelization or highly expensive, deterministic security. Selecting a 2026 model acts as a foundational architectural decision, determining the survival of an engineering organization far beyond a standard software subscription. We start with Moonshot AI's Kimmy K2.5, a 1 trillion parameter model built on a philosophy of extreme economical parallelization. This diagram illustrates Kimmy's agent swarm execution scheme. Rather than holding a linear conversation with a single AI, the system dynamically splinters a complex assignment into a vast web of 100 domain-specific subagents that all process data simultaneously. By operating in parallel, this swarm cuts execution time by a factor of 4.5, resolving nearly 77% of software bugs on its own. The economic advantage here is severe. Kimmy K2.5 charges roughly 50 cents per million input tokens. API pricing is the fee developers pay a provider to process data, usually calculated per 1 million tokens of text. At 50 cents, Kimmy severely undercuts proprietary models, enabling huge task volume on a startup budget. The trade-off for that price requires relying on decentralized inference infrastructure, meaning the model is hosted across multiple independent server networks rather than a single corporate data center. It also demands that you trust a fully autonomous swarm to act with minimal human oversight. Kimmy K2.5 also possesses native multimodal capabilities. Because it was trained on both visual and text data simultaneously, it excels at a process developers call vibe coding. You can feed the model a raw video recording of a complex animated user interface. The AI analyzes the 3D elements and spatial relationships in the video and autonomously drafts the required front-end code to replicate the design. This removes the traditional translation step, where a software engineer has to painstakingly interpret a UI designer's text-based specifications. By combining visual inference and swarm execution, Kimmy K2.5 allows budget-constrained startups to operate with the output of a massive engineering firm, provided they're willing to yield micro-level control to the system. For organizations requiring strict control, Anthropic designed the Claude 4.6 family, with Claude Opus 4.6 acting as the premium standard for massive enterprise environments. Anthropic implements its own multi-agent architecture known as agent teams. Instead of a fully autonomous swarm, these teams are structured specifically to tackle independent, read-heavy work, like codebase reviews and large-scale security audits. This organizational chart shows Anthropic's mandatory human-in-the-loop design. A developer can intercept, monitor, and take manual terminal control of any active subagent at any time. This design choice is driven by direct behavioral data. While engineers frequently use AI, internal research shows they only feel comfortable fully delegating 0 to 20% of high-stakes tasks. Beyond human oversight, enterprise tasks carry a severe technical hazard. Feeding millions of tokens into a model over a long horizon inevitably causes attention drift, memory thrashing, and logical failure. To survive these long operations, Opus 4.6 uses context compaction. The model proactively summarizes its own historical state, compressing highly granular information into dense, summarized representations, so it stays within operational limits without losing focus. The financial trade-off for this reliability is immense. Claude Opus 4.6 operates at a 10x multiplier compared to OpenWeight's models, costing $5 per million input tokens. Because of this overhead, engineering teams must carefully adjust the model's manual effort controls to dictate exactly how much computational thinking the AI performs, balancing intelligence directly against the IT budget. Claude Opus 4.6 functions as an autonomous technical project manager. It buys enterprise leaders safety, reliability over long horizons, and strict human oversight, but it comes at an absolute premium price. OpenAI's GPT 5.2 Codex takes a completely different approach. It acts as a direct philosophical rejection of the speed-first, autocomplete style models that previously dominated the market. This process timeline breaks down the model's core architectural shift, System 2 reasoning. Before GPT 5.2 generates a single character of output, it stops and simulates its logic internally. During this simulation phase, the model performs deep abstract syntax tree parsing. An abstract syntax tree, or AST, is a hierarchical map that represents the exact logical structure and dependencies of source code. The model maps this tree out entirely before it acts. By simulating the code first, the model guarantees its output strictly adheres to existing architectural patterns, which virtually eliminates the subtle state management bugs that cost senior engineers hours of debugging. This dense reasoning gives GPT 5.2 a specialized dominance in defensive cybersecurity. The model has an unparalleled capacity to identify deep zero-day vulnerabilities. A zero-day vulnerability is an undisclosed software flaw that hackers can exploit before the developers even know it exists. The workflow trade-off here is patience. GPT 5.2 Codex acts as a slow, deliberate architect rather than a rapid typist. It explicitly sacrifices instant gratification to guarantee absolute determinism, making it the only viable choice for organizations migrating zero-risk legacy codebases. Raw parameter scaling is over. Your choice of a 2026 AI architect depends entirely on your specific organizational constraints and your tolerance for risk. This flowchart maps out the final strategic evaluation framework for the year, starting with one prompt. What is your primary engineering constraint? If you manage enterprise SecOps dealing with mature, heavily regulated code or defensive cybersecurity, you follow the first path. Your requirement is OpenAI's GPT 5.2 Codex. Its deep System 2 reasoning is a non-negotiable asset for maintaining strict architectural accuracy and zero-day protection. If you are a rapid-scaling startup, a DevOps team, or a visual-first UI developer, you follow the second path. Your choice is Moonshot AI's K2.5. The 50-cent unit economics and native vibe coding make massive swarm parallelization a reality on a tight budget. Finally, if you run a large general engineering team requiring reliable, long-horizon knowledge work, you take the third path. Your architect is Claude Opus 4.6. Its agent teams strike the necessary balance between deep logic and essential human-in-the-loop oversight. In the era of autonomous software engineering, the priority has moved to risk management. You must choose your model based on the cost of a mistake, not the speed of the generation.